Page 7 in the notes, and I'm going to go through this first part fairly quickly because this is what we did at the beginning of the unit. We have already graphed quadratics using these graphing strategies, and the big things that we covered in the first part of this unit was the key features of a parabola. The first being the axis of symmetry, which is on here. A of S is x equal over 2a. That is this imaginary line right here. The vertex we get from this negative b over 2a and plugging it into the equation. So the axis of symmetry takes us to our vertex. Then our y-intercept is always the c value in our standard form equation. Sometimes it's a nice point, sometimes it's not a very nice point. And then the x-intercepts. For graphing, we had to catch the x-intercepts in our table. So catch in table. Why wasn't this always very efficient? It takes a while. It takes a while to do the table. We don't know how many points we're going to need to catch those x-intercepts. And also, for graphing, sometimes we got those between values. So graphing is our first method of solving quadratics, but the issue is it's not exact. And it only shows the integer roots. And time consuming, which is important to us. We don't want to do something that takes too much time when there are easier things to do. So not exact, only shows integer roots, and it's time consuming. Now, our second method of solving is factoring. Hopefully, after all of the activities that we did last week, you're starting to feel a bit better about factoring. The limitations that we have for factoring, though, is it only shows real solutions. So only real solutions. No imaginary nor irrational. Completing the square. We're not doing that. Total waste of time. It's such an annoying way of solving that we don't even mess around with it. The third, which we haven't talked about yet, is the almighty quadratic formula. This finds any solution. We may start that tomorrow. It's a big old formula. There it is. But not only is it kind of tricky to use, it's pretty tricky to simplify, but the benefit is that the quadratic formula can find imaginary, irrational, and integer solutions. So folks, what we're going to be doing is we're going to be kind of comparing and contrasting all three of these methods so that we can look at a problem and determine what's going to be our best course of action for solving. So first, to solve using any of these methods, the quadratic needs to be in standard form, ax squared plus bx plus c equals 0. So to solve using any of these methods, we want this. Now, for factoring, A must be positive. It doesn't have to be positive for the other methods, but you'll find that your work is a little bit easier if it is positive. So down at the bottom, we are going to start by reviewing how to graph quadratics, since that was a long time ago last week, and how we can use that for solving. So the first thing we check for is standard form. Is this in standard form equal to 0? Yep, looks good. So the next thing we want to find is our axis of symmetry. So our A of S, axis of symmetry, is x equals, anyone remember the formula? Negative b over 2a, there it is. And what's nice is, negative b over 2a is actually part of the quadratic formula. So when we learn the little song, you're going to have a way of remembering the axis of symmetry formula. So our b value is 8, so negative 8 over 2 times our a value of 1. So negative 8 divided by 2 is negative 4 equals x. Why do we need that equals x? Because it's an equation for a vertical line. So we're going to go ahead and put a dashed vertical line going through negative 4. And what this tells us is that our vertex is somewhere on that line. Maybe it's at negative 4, 0. Maybe it's at negative 4, 4. Maybe it's at negative 4, 8. How do we find the corresponding y value of the vertex if we know that the x value is negative 4? How do we find the y value if we know the x value? Plug it in to the equation for x. So I'm going to center my table. Let's make it a little bit longer. We're going to center it around the vertex x value, which is negative 4. Now I'm going to plug that into this equation for x. What's already not okay with how I have this entered in on my calculator? Parentheses. Anytime you're plugging in a negative number, make sure that you're trapping it in parentheses. Otherwise, you're going to have a bad time with that exponent. So negative 4 squared, arrow over to escape the exponent, 8 times negative 4. Folks, go ahead and grab a calculator off the cart if you need one today, or grab yours out of your bag. And we get negative 9 for the vertex. So negative 4, negative 9. Oh, I'll charge you. So now, to get 4 other points, we're going to go a few values less than negative 4, like negative 5 and negative 6, and a few values greater than negative 4, negative 3, negative 2. What's our little shortcut for copy-paste on the calculator? Second enter, hooray! We're going to override those negative 4s with negative 6s. And that gives me an output of negative 5. Second enter. We're going to override those negative 6s with negative 5s, which gives us negative 8. All right, folks. Now, what should negative 3 give me for an output? Should give me negative 8. We should be getting those symmetric y values around that vertex, but we're not going to assume it because sometimes we make mistakes with that axis of symmetry. So I'm going to go ahead and just verify it by overriding those negative 5s, negative 3s, and we see that we do indeed get negative 8, which means this would give me negative 5. So we've got that symmetry around the vertex. I'm going to go ahead and plot those other points. Negative 5, negative 8, ignore that one. Negative 3, negative 8, negative 2, negative 5. Have we caught the x-intercepts yet? No. Are we going to get x-intercepts? If I curve through that U, we're heading for the x-axis right there. So we haven't found them yet, but there definitely are going to be 2 x-intercepts. So let's go a little bit further this way with negative 7. And a little bit further this way with negative 1. Second enter, replace those negative 3s with negative 7s. And we get 0, right on the money. So negative 7, 0, and negative 1, 0. And we can stop there because we have found the x-intercepts. Holy cow. So negative 7, 0, and negative 1, 0. So how we'd write our answers is we'd say that x equals negative 7 and x equals negative 1. So did solve by graphing work? Yep. And we found the roots exactly. So that was method 1, solving by graphing. Method 2 is solving by factoring. So folks, let's see what happens when I tried to solve this by factoring. So same equation, just wrote it down below. Do we have a GCF? Nope. Do I have to use the x method? Coefficient of x squared is 1, so we're good there. So I'm looking for a product of 7 and a sum of 8. What are my two numbers? 7 and 1. So if I have something times something equals 0, that means either this something is 0 or this something is 0. And what do I get when I solve those two mini equations? We subtract 7 and we get negative 7. We subtract 1 and we get negative 1. Did we get the same x-intercepts? Yeah. Was it a lot less work? Yes. We still need to understand what we're solving for. What we're trying to find is the x value that makes that y value equal to 0, but factoring is much faster. So let's go ahead and take a look at this next one. Looking at that equation, what's our first beef with it? Not in standard form. So let's keep our a value positive, which is right now. And let's add that 2 over to the other side. That way we'll have 2x squared minus 8x plus 2 equals 0. Before we solve by graphing again, let's try to solve this one by factoring. Down at the bottom, we get 2x squared minus 8x plus 2 equals 0. What do you want to do first for this one? GCF makes life easier. Then we don't have to do the x method. So x squared minus 4x plus 1. So now we're looking for a product of 1 and a sum of negative 4. Uh-oh. Can we do this? Nope. So this one is prime, which means we can't find the solutions by factoring. What are those two types of solutions? Imaginary is 1, so maybe imaginary. What's our other possibility? Maybe irrational. Because remember, those irrational ones are just nasty square roots. I can see them. They are decimals, but they are not friendly decimals like 0.5 or 3/4 that we can find by factoring. So this is all that factoring told me. So yeah, factoring is fast, but we don't know from factoring what types of solutions we're trying to find. So now we go back to the drawing board and let's go ahead and factor. No, let's not factor. Let's find the axis of symmetry. Oh boy. So our axis of symmetry is x equals negative b over 2a, making sure you're using that standard form equation. So negative 8 over 2 times our a value of 2. This gives me 8 over 4, or x equals 2. Make a nice big xy table. And center it around that vertex x value of 2. Using your calculator, I want you to find the vertex y value and at least 4 other points more if necessary to try to catch those x-intercepts. 1, 2, 3, go. Folks, is 0, 2 an x-intercept? What is that? That, my friends, is the y-intercept, which, notice, matches your c value. On this one, our y-intercept would have been right here, so maybe my graph's a little sloppy. It should have been going up through that point. Your y-intercept is not always going to be a useful point, but it is another exact point that you can find. So 0, 2, that's not my y-intercept, but there it is as a point. 1, -4, boink. 2, -6, 3, -4, and 4, 2. Have we crossed the x-axis? Yeah, but did we find the x-intercepts? No. At least not exactly. So these were the ones that were a little bit tougher to express. We see that we go from a positive y value to a negative y value. Positive down to a negative. That means somewhere in between those, we hit a y value of 0, which means somewhere in between those x values, we found an x-intercept. Same with here. We go from a negative to a positive, so somewhere in between those two values, we had an x-intercept. You can also kind of just guess it from the grid marks as well. This is between 0 and 1. This one's between 3 and 4. So x is between 0 and 1 and between 3 and 4. So yeah, we don't like graphing, but this gave me a better idea about my solutions than just solving by factoring. So because of this, which of these maybes can we get rid of? It's not going to be imaginary, because remember, those imaginary ones we can't see at all. So this verifies the combo of these two, that my solutions would need to be irrational. Yeah? Turn the page. And we've already been doing solving by factoring. So we're just going to be doing the same thing on this page. Method number 2, we're not going to try to graph these at all. We are purely going to try to solve by factoring. Step number 1, make sure the equation is in standard form with a positive a value. factor completely, set each factor equal to 0, and solve for x. All right, folks, I'm going to turn you loose on those 4 problems. See if you can factor them. Folks, how many of you are stuck on A? A is weird because there's no what? There's no C value. So if you're like, oh my gosh, am I looking for a product of 0 and a sum of 20x? It is in standard form, that's good. What's the very first thing we check for when we're factoring? A GCF. And here, folks, not only can I take out 4, what else can we take out? An x. So here, the GCF is actually your only method of factoring that one. So always, always, always check for a GCF first. So then that leaves me with x plus 5 equals 0. So now, 0 product property time. I have something times something equals 0. So either this 4x is equal to 0 or this x plus 5 is equal to 0. In which case, x would be equal to what? 0. If we divide 0 by 4, we get 0. Or negative 5. Would we be able to see these solutions graphically? Yep. So I know it's a happy graph. I know that one x-intercept is here. The other one is over here. 2, 3, 4, 5. We don't know exactly where the bottom is or where the vertex is, but there's my happy graph with my 2 x-intercepts. We know that we would be able to find these using a graph. So taking a look at B, before you're like, oh, different squares, what's the first thing we should check for? GCF, and we can take out a 4, which leaves me with x squared minus 9. So now I have difference of squares. Square 9. So 4x plus 3 and x minus 3. Perfect square factors of x squared, x and x. Perfect square factors of 9, 3 and 3. One gets a plus and one gets a minus. So now I have 4 times something equals 0. So either x minus 3 is 0 or x plus 3 is 0. Hey, can 4 be equal to 0? Sometimes Monday brain goes, wait, what? Can 4 be equal to 0? This over here, this GCF could be equal to 0, but why? Or rather x, it has a variable with it. So any term that has a variable with it, we set equal to 0. But 4, that's just the number 4. There's no way for it to be equal to 0, so we just leave it alone. And our solutions would be x equals 3 and x equals negative 3. And once again, solving by graphing would yield an x-intercept over m and an x-intercept over there. We don't know where the vertex is, but we know it would look like this. All right, folks, take it from here. Try C and D. Product of 64, sum of negative 16. What are we thinking? 8 and 8, both negative. So our factors would be x minus 8, x minus 8. Interesting. Because I have the same two factors. So something times something equals 0. Well, either this one is 0 or I guess that same one is 0. And we get x equals 8 and x equals 8. Folks, how many solutions is that? It's just one, really. So think about a quadratic intersecting the x-axis in one spot. How does it do that in only one spot, thinking about symmetry? Yes?
It goes down, and the lowest it ever goes is the x-axis.
Wonderful. The lowest it goes is the x-axis, which means our vertex is the x-intercept. So, 1, 2, 3, 4, 5, 6, 7, 8. So if I only get one solution, the only way that that can occur is if my parabola is sitting on the x-axis. Folks, let's go back in time to the last unit. If I were to write this in condensed form, it would be x minus 8 squared. What does even multiplicity tell us about the behavior of the x-intercept? Does it bounce or does it cross? It bounces. And that's exactly what my vertex does. We go down, boink, and then we come back up. So it's starting to come together full circle of how the last unit ties together with this unit. Why those factors have an opposite sign from their x-intercepts and what that's going to look like on our graph. All right, folks, next one. What do we need to do first before we try factoring it? Standard form, swing that 5 over. So 12x squared minus 17x minus 5 equals 0. Ooh, is there a GCF? That makes me very, very sad. There's no GCF. And why I'm so sad is 12. How many different pairs of factors do I have for 12? 1 and 12, 2 and 6, 3 and 4. Boo! Now, at least for 5, that end one, we only have 2 possibilities, but let's go ahead and start with factors of 12. I normally start with the numbers that are closer together, like 3x and 4x. Let's just see what that does for us. Factors of 5, 1 and 5. Multiply crisscross, x method. We get 15x and 4x. Did that work to give me a sum of negative 17x? Nope. I'm going to flip the order. Let's try 5 and 1. 3x and 20x. And oh, thank goodness. Only took us 2 tries. Folks, what do I need to do to these so that I get negative 17 for the sum? Make the 20 negative, which means making the 5 negative. Now, don't forget, it's always in your interest to check the product number before you write the factors. Is negative 5 times 1 negative 5? Yep. So that means our factors going straight across from each other. The 3x gets paired with the negative 5. The 4x gets paired with the 1. So, wish we had more room. 3x minus 5, 4x plus 1 equals 0. So either this factor is equal to 0, gross, or this factor is equal to 0. Add the 5 over. 3x equals 5. Divide by 3. Ew, x is 5/3. Not my favorite x-intercept. 4x equals -1. X equals -1/4. Also, not my favorite x-intercept. Hey folks, would we be able to find those solutions by graphing? We'd be able to see them. We'd be able to see that this does have x-intercepts, but we'd be saying x is between 1 and 2, and x is between 0 and -1. So we wouldn't be able to find those exactly by graphing, but we would be able to see them. And now for your enjoyment, you can cross off the entire bottom part of this page. Completing the square is a strategy we'll use to write equations in vertex form. That's going to be in Unit 4, Part 2. But that is where we are going to stop for today. And actually, you can cross off those 3 problems up at the top as well. Up at the top of the next page, those 3 problems are gone too. And we'll leave the quadratic formula for tomorrow. So, folks, work on completing numbers 1 through 12 in the homework packet. So those complex numbers. Don't do anything with the next section. This just, well, I guess you could. Folks, here's what you can do on this section if you so desire. If you want to start working on these problems, the solve quadratic equations, you can try to factor. And if you can, solve it. If prime, leave it. So try to factor those, but if it's prime, leave it. So we've got a little bit of a larger chunk of work time for today, so I would definitely try to get through 1 through 12 and then start putting these in standard form and trying to factor them. Yes? No, let's stay in here for today in case you have questions.